Rajwal from Sri Venkateswara College of Engineering, Department of ISC. Today my topic is based on technical seminar, that is natural language based human machine collaborative learning games algorithm based on deep reinforcement learning. We're gonna learn today. These are the contents of this thing: introduction, related backgrounds, working and implementation, future enhancement, conclusion and reference. The introduction provides an overview of machine learning collaboration, where humans and machine work together to achieve common goals and maximum benefits. It highlights the integration of human perception and reasoning into machine decision-making process, emphasizes the importance of continuous optimization through feedback mechanisms. Furthermore, it discusses the widespread application of human-machine collaboration in various fields, particularly in open dynamic environment like electronic games. Electronic games serves a typical environment for simultaneously intelligent decision-making problems based on different rules and scenarios. In this context, deep reinforcement algorithm, that is also known as DRL methods, such as the open purpose in study, are commonly used to learn optimal behavior strategies through interaction with the environment. It introduced the concept of natural language reward construction as a means of optimization (DRL) and improves the agent decision-making abilities to incorporate human prior knowledge and achieve ultimate goal to enhance the agent perception, reasoning, and decision-making in electronic games environment. Backgrounds. It discusses the current status of DRL, that is deep reinforcement learning, and the challenges faced in sparse reward environment. Traditional DRL method heavily rely on environmental feedback information for network parameter calculation, making it difficult to learn effectively strategize in scenarios where rewards are scarce. To address this limitation and enhance the human-machine collaboration ability of video games agents, the study proposes the use of natural language reward construction to optimize DRL. By introducing human prior knowledge into decision-making process of agents, the algorithm aims to improve their perception and reasoning abilities with electronic games environment. Overall, the related background highlights the need of innovative approaches such as natural language based algorithms to optimize DRL in sparse reward environments and improve the decision making abilities of agents in interactive settings like electronic games. Let's get to working and implementation. It introduced a novel algorithm based on deep reinforcement learning to enhance the exploration and decision-making abilities of agents in sparse reward environment. The algorithm utilizes natural language instruction to guide the reinforcement learning process of the agent, aiming to improve their performance in electronic games environment. Furthermore, the study introduces a high site experience relay algorithms to optimize the natural language reward construction model. This optimization approach addresses the challenge of sparse reward by enhancing the reward effectiveness of human-machine collaborative agents. Through experiments, the design model achieves high scores in games and demonstrates a high prediction accuracy, showcasing its effectiveness in sparse reward environment. By combining DRL, natural language instruction, the hint site experience replay, the algorithm offers a promising solution to improve the collaborative between humans and machines in interactive settings. The research aimed to advance the field of human-machine collaborative technologies and add a valuable insight for further development and optimization in this area. To understand this working and implementation, here is the schematic diagram of language reward model. In the context, the gaming environments, CNN and LSTMs can be used in different ways to process input data and make decisions with the game environments, where CNN plays a vital role as visual input processing, feature extraction, and LSTMs process such as temporal modeling and language processing. Integrating of these both CNNs and LSTMs, we can make a hybrid architecture. In summary, CNN and LSTM plays a complementary role in gaming environments, with CNN typically handling visual input processing and feature extraction, while LSTMs excels at modeling temporally dynamic and process sequential data. Integrating these both architectures can lead to most powerful gaming agents capable of handling diverse types of input data effectively. Taking the example of a game, here's how CNN and LSTMs could be used in this game environment. CNNs for visual input processing such as game frames and feature extractions. Game frames where each frames of the game displays the characters, surroundings and obstacles can be input to CNN for feature extraction. The CNN learns to recognize different elements of the game environment such as ladders, steps, obstacles and keys. Feature extraction. The CNN extracts meaningful features for the raw pixel data such as edges, textures, and sharps shapes, which are then used to represent the game state. LSTMs for temporal modeling, such as action sequence and log-term dependencies. The player actions such as climbing the ladder, jumping up the steps, or sliding prone under obstacles from, from a sequence of events. As LSTM can model the temporary dependency between these action learning patterns and strategize for navigating through levels. Long-term dependency such as can capture long-term dependency between action, allowing the game agents to understand the sequence of processing action and plan future moves accordingly. Okay, this is the performance analysis of natural language human machine collaborative learning games based on improved deep reinforcement algorithm. So learning. So this is the experimental environment and this is natural language instruction. Experimental environment consists of the hardware and version types, where environmental operating environment is AMD Radeon 56400G at 4.8 GHz, memory of 64 GB, operating system that is Ubuntu 18.0, and language type is C++ language. Experimental platform is PyTorch, and natural language instruction is the keys which are specific for making the action label. We have used A for climbing the ladder, B for climbing down the ladder, C for jumping over the obstacle, D to prone slide obstacle, E to jump up the steps, F to jump and get the keys. Has revolutionized gaming agents by enabling them to learn directly from raw sensory input such as pixels and make decisions in complex environment. Some of the agents are deep queue networks, that is DQN, double deep queue networks, DDQN, deep deterministic policy gradient, that is DDPG, proximal policy optimization, PPO, trust region policy optimization, TRPO, asynchronous advantage actors critic, that is A3C, soft actor critic, SAC. So in this figure shows that the scores of different algorithm agents in game and shows the scores of LA2C, DNQ, DDPG, PPO, A3C and NEC algorithm agents in the game respectively. The LA2C agents could achieve higher score in the game up to 9.8 points. It is followed by DDPG, DNQ, NEC, PPO, and A3C with highest score of 8.7, 8.5, 8.2, and 7.0 and 6.8 respectively. This is the graph of accuracy achieved by different algorithms agents in game instruction target. The graph is accuracy versus number of experiments, where HLA2C have achieved the more times. So coming to the result, environmental reward change curves under different algorithms. This shows the variation curves of environmental rewards under different algorithms. HLAC2 could obtain higher environmental rewards in sparse reward environments, indicating the HLAC2C could obtain higher reward feedback and develop effective behavioral strategies in sparse reward environments, because HLA2C could obtain more effective feedback from natural language instruction through HER algorithm and rely on reinforcement learning ability to correctly follow natural language instruction, thereby reducing the ineffectiveness of action. As the number of image frames increased, the environmental rewards of these 6 algorithms also gradually increased. With 800 frames, the environmental reward of HLC could reach up to 9.8, where and A2C could achieve higher environment and reward of sparse reward in sparse reward environment. These are the final game scores of different models. This figure shows the final game scores of different models, where HLAC2 had higher game scores because HLA2C could obtain higher environmental reward through natural instruction in sparse reward environments. Environmental rewards could facilitate the agents to develop correct behavioral strategies, thereby improving the accuracy of agents' behavior in sparse reward environment. High behavioral accuracy could encourage agents to score in-game and reduce the risk of losing points. In both training and testing experiment, HLA2C could achieve higher game a score of 9.9 and 9.6 respectively. Further analysis showed that HLA2C performed better in sparse reward environment, mainly due to its unique design combining natural language reward, constructing the HER mechanism, and the HER mechanism greatly enhanced the model learning of sparse positive feedback of revisiting and learning from failures. These are the future enhancement. Future research could explore a wider range of gaming environment to access the applicability and effects of models in diverse settings. There is a room of further optimization in natural language processing aspects of the study. Future research can explore more advanced natural language understanding technique to improve the understanding ability and response sensitivity of agents. Further study could focus on understanding human user intention and preferences more deeply. By gaining a better understanding of user behavior and intentions, the agent's decision-making process can be further optimized to better match the user's needs and expectations. Further research could aim to develop deeper understanding of user intentions and preference to optimize the agent's decision-making process for important satisfactions and process. Coming to conclusion. In conclusion, by incorporating natural language instruction and hindsight experience replay, the algorithm demonstrates significant advantages in improving accuracy, efficiency, and decision-making capability of agents in electronic games environment. The research finding highlights the algorithm effectiveness in addressing the limitation of traditional human-machine collaborative models and extending the application of DRL in natural language understanding collaboration. The study contribution in optimizing task execution, enhancing learning efficiencies, and providing a richer interactive experience, pave the way for future enhancement in exploring diverse gaming environment, optimizing natural language processing techniques, and deepening the understanding of human-machine collaboration. Overall, the natural language-based algorithm shows promises in advancing human-machine collaboration technology and offers valuable insight for further research and development in interactive systems and educational settings. So these are the references. Thank you.